forward to that.
It's now a great pleasure to introduce Rich Sutton, who was my thesis advisor and has done lots of work at the interface of computational intelligence as well as neuroscience and representations of intelligence there. So we're really looking forward to his perspective.
Thank you, Dyna, for introducing me. It's a great pleasure to be here with y'all. Gosh, I stayed up late preparing my talk and obsessed over everything. And then I came to the meeting and I decided I had the wrong talk. And I started all over again. Of course, I built on existing talk, so it's not going to be terribly disorganized what I'm going to present you today, but it's sort of fresh. The ideas are new. They're workshop-style talks. You won't find a publication on these ideas. So, I don't know, pay attention. I guess it also, I've accumulated a few affiliations as of late, and I just want to dedicate this talk to the Alberta Machine Intelligence Institute, or AMI, because I'm wearing their t-shirt. Hope you can see that. Okay. So we're going to talk about this ambition of a general AI agent. This would be appropriate for biological reinforcement learning or artificial reinforcement learning. There's sort of a working name, we call it Super Dyna. That will not appear in the publication. That's just sort of informal. It expresses the ambition of taking on the Dyna agent from 1990 and making it more capable, adding things that are obviously missing from it, and then also trying to go even farther than that to make a more complete agent. The word general is also going to be important here. But let me go ahead and just sort of give you a quick outline. These are the things we're going to talk about to help us keep each other straight. You're going to see me talking about predictions and planning and subproblems, and then try to make this pseudocode of Super Dyna sort of a template algorithm, putting everything together. Okay, so the premise is, first of all, we seek general principles for learning to predict and control experience. Learning to predict and control experience, that's what intelligence is. That's my premise. And by general principles, I mean the domain-independent part. Things that don't depend upon the particular world, doesn't depend on people or objects or even space. It will depend on time, because every world has time. But we want to be very general to the world. We know so the domain-independent parts of intelligence are obviously important to get good performance, but they're not the subject of this talk. They're not the subject of this ambition to make a general agent. Okay, we will adopt the standard goal of reinforcement learning to maximize a reward. Maybe this is necessary. Anyway, it's adequate. But of course, most learning will not be about reward, not solely reward. Of course, we presume we're going to need function approximation. That's what we've learned from the years of deep learning. We need to have highly parameterized function approximators. We need partial observability and temporal abstraction and non-stationarity. Let's look at these things a little bit one by one. Well, first, let's start with this basic point of view that the world is big. It's like much bigger than the agent. It's like totally unlike Atari. Atari is, you've got this whole world that fits in like 4K on a little computer from long ago, and then you apply to it like all of Google scale compute, And It's just the opposite. And I think that warps things a little bit. Really, the world is much larger than the agent, and this implies that function approximation is not just a sort of a temporary thing, but it's permanently, even at the end, you have just a really crude approximation to the ideal thing. Now, because this also is going to make the world appear non-stationary, because the world's really complicated. You're seeing one part of it, and later you might see another part of it. And so even though the world may be stationary, your approximations are going to be non-stationary, because your approximations you want to adapt to the part of the world that you're encountering. This theme is going to come up a few times. The world is effectively non-stationary. Okay, partial observability. Well, let's look at the standard reinforcement learning diagram. Oh, I'm really happy. I think you can all see the bottom of the slide. So I'm going to put a few things across there. The standard diagram, we have an agent interacting with an environment, and environment has got like 4 syllables, and I can't say it, so I'm just going to call it world. The agent is a policy and a value function, perhaps, and it sends actions to the world sends back a reward, and it sends back the next state. Okay, that's the standard view, but we want to get rid of this assumption of state. Right? We take the assumption of state throughout the reinforcement learning textbook that Andy Bartow and I wrote, but we really want to get beyond that. So the world is not going to produce state. Maybe the state of the world, it's huge, right? It's complex, much more complex than I am. How could I even receive such a thing? Instead, I'm just going to get partial information. So the word is observation. We assume we see an observation. So then it's up to the agent to convert the observation into a state. So that little box and that little process that I'm naming state update is the process of updating my state based on the most recent observation and the most recent action to produce the next state. And so we're going to need that. It fits neatly here in our diagram, and it's almost like the rest of the agent doesn't need to be changed because it receives an apparent state. But this state is now the agent's estimate of the state of the world. It can be a very small thing. It can be a summary thing. It should be a feature vector, which we're going to do function approximation over. Okay. So next, I am presuming that all the learning is going to be online learning, and it's going to be temporal difference prediction learning. Well, there'll be a little bit of control stuff, but it'll basically, we can think about so much of the learning being just online TD prediction. It'll be long-term, it'll be action conditional, and we have a very general form for it now called general value functions. Okay, now, we need to construct 4, well, specific mental components, general mental components. And these are, in addition to the usual things like the policy and the value function, we need to construct the features. We need to construct subproblems. More and more about that. Remember, that's on my outline. We need to construct solutions to the subproblems. So these are the form of options. So let's see, I guess I have that. Options enable us to do my 4th desiderata, to do temporal abstraction. Options are just a policy and a value function. So you see I'm pointing down to the, if this works, yeah, it kind of does. I'm pointing down to here before we had just one policy and one value function. Now you have a bunch of policies and value functions. And for each one of those is like a subproblem to achieve some subgoal, which I'll talk about. But once you phrase those subproblems, the option is the solution to that subproblem, the policy that's specific to that subproblem, the value function that's specific to that subproblem. We form lots of these, and this gives us higher-level ways of, higher-level behaviors to think about. I could think about, going to the coffee room or going back to the hotel or picking up my arm. Because even small things are really made up out of many, many time steps and many, many actions. Okay. The last step is we need the world model because we need to plan. We need to plan. That's an essential part of intelligence. So the last picture suggests the role of the model and the planner is they kind of sit on top of everything, and I learn the model and then I plan with it. I'll talk about that. But it has to be in terms of components 1 through 3. It has to be in terms of the states, in terms of the options, that are the solutions to the subproblems. Okay, so that's the basic perspective. Oh, one last thing is that in some sense, what I intend the things listed here to be basic needs. You got to have a model. You got to have temporal abstraction. You got to have function approximation. These are meant to be just basic things. And the ambition of SuperDyna is to attain all of these basic things in one architecture. Okay? And so to attain all of them, even though they're each simple, is unprecedented. And it's a good, ambitious goal. Okay. Now let me just say a little bit. I can only just do this one slide about the state update process. The state update process is going to be feature-based. We're going to have to find good features, and that will be representation learning because the state is the most important representation in a reinforcement learning agent. And that state construction process, or updating process, is a recurrent process. You can see from the equation at the bottom, the new state is some function of the old state in the action observation. It's recurrent. And we imagine that there's a recurrent network with a big, wide feature vector, millions of features, candidate features. Maybe only some of them are proven good, but there's a lot of them to begin with. And that is updated in a recurrent nonlinear process to construct really good features. And then the predictions that we're making with TD learning are all going to be linear. They're going to be general value functions, GVFs, and they'll be linear functions of the state representation. Now, the features are found by some combination of gradient descent and search, and I have a lot of ideas about this, but it isn't really settled yet. Some of it will be search, generating a lot of things and testing selective survival. And in the end, we will rank the features by utility, and the most used features will become targets of the subproblems. Subproblems, remember, is coming up. But first, I want to talk about planning. Planning, the Dyna architecture was just the idea that you could have this interact with the world, do reinforcement learning, and then unplug the world and plug in the model, and just keep going. And it was essentially the same process. So this is the standard demo of Dyna, and that little algorithm up there is really a pretty good description of the whole idea. And I'm always happy that I can express an algorithm that does both learning and planning and interacting with the world all in one slide and one little pseudocode. So our agent is starting at the start and getting a reward when it reaches the goal. And the green represents how happy it is with each state that it's running into. And the arrows are also in the agent's mind. They represent what it plans to do there. It's like a stimulus response map. And because it's a planning agent, which means it's learning a model, the model is something like, if I'm in square 16 and I do action 3, then I'll end up in square 64. Okay, so it's all tabular. Everything is a table. The value function is a real table, and the policy is a table, what to do in each thing. But because it's a planning agent, when it does eventually stumble on the goal, it will plan a route there very quickly. Even without going through all the states, it plans a route to get there. So that's sort of Dyna, if you haven't seen it up to now. So Dyna is based on a kind of planning. The planning is just, here I am in a state, or rather, here I am imagining I'm in a state, and here I am imagining an action. What do I think will happen? I'll pretend it did happen. I'll learn from it. More generally, we can talk about dynamic programming style planning, which means you use the model to look ahead, imagining something, and that's called a lookahead. And then after one or more lookaheads, you do a backing up process. So these kind of diagrams are maybe familiar to you from the reinforcement learning book, but we see states, the open circles, and actions, the closed circles. And what is the look ahead? I'm using this kind of childish word, look ahead, just because I don't want to have to define a new word. So what are the look aheads? Each imagining, it's funny, we don't have a word for this thing. If you have a model, and you want to, what do you do with the model? Well, you use it to guess what's going to happen. So what is the step of guessing what will happen? There's no word for that. So I'm making up words for it. I used to call it a projection, but that sounds like math. Anyway, it's a look ahead. It's a look ahead. So if you look at these pictures, where are the look aheads? Which part of them is the look ahead? Well, the look ahead is, in the first diagram, are those three things, because that's a state action pair, and I'm looking ahead to what state and what reward might result from that action. And in the other diagrams, the projections, well, first here's the backup. The backup is from the leaf nodes back up to the top state. And for the other case, the look-aheads are, when we have a diagram that's a straight line like that, it's often a sample sort of look-ahead rather than a distribution look-ahead. Anyway, we do the backups. We can back up from 2 steps, or we can do 2 separate look-aheads and 2 separate backups. In either case, you get planning by just doing backups forever. This gives you a general kind of planning. You can do anything you might want to do with planning just by doing these little backups in various combinations. Okay, now what is let's be more specific. What is the output of a look-ahead? This basic process of a model guessing what's going to happen. Are you going to get because the world is stochastic. So what are you going to guess? You could guess the whole distribution, call that a distribution model. But what if the states are going to be, well, our states are going to be real valued feature vectors. We want to have function approximation and everything. The states are not going to be unitary. They're going to be a whole feature vector. And so how do you get a distribution over these feature vectors? And then how can we work with that efficiently? It's challenging. And how could you roll it out? Like, how could you do 2 steps? You look ahead 1 step, you get a whole distribution, and then if you want to look ahead farther, you can't look ahead from a distribution. You could look ahead from every element of that distribution, and then it becomes really complex because you're branching. Okay, another approach is to do a sample model. A sample state, like in Monte Carlo tree search, you get one possible next state, and then you can roll it out because you can go to that next state and say, where could I go from there? This saves you from generating the distribution, but you still have to have the distribution. You still have to sample from something and somehow generate from the appropriate distribution. Also notice that in this case, planning becomes stochastic. Okay, now the third case is actually the one that I like, so I'm saving it for last. The third case is called an expectation model, where you don't generate an individual feature vector, but an average of possible feature vectors. And this also cannot be rolled out because you generate an average, it's not really an entity so that you can look forward from. But learning is straightforward, the process is deterministic. In general, we lose information, but not in the special case of linear value functions. So let me show you that. So this is the equation for general value iteration with a full model, a full distribution model. And it really corresponds to that diagram. So the algorithm is really starting here at the top, and we're gonna consider the max over all the possible actions. That's this max over. It could be an action or it could be an option, so I call it O. And then there's a sum over all the possibilities. That's this branching factor. Okay, so that's the basic idea. We're going to do this diagram as an equation. And we're going to represent the value function for a state as a linear form. So that means it'll be W times X, the inner product of a weight vector and a feature vector for state S. So that's how we will represent this approximate value function. Okay, in the update, this just means we're going to adjust the weights so that whatever we get on this side so this is moved towards the right-hand side. Okay, so we get the reward, the reward, and the sum over the possible next states, because that's a distribution model, gives us the probability of each next state. Okay, so this is just value iteration, and it does planning just fine. It's exact. And what I wanted to show you is that we can get the same thing as this if we have a linear value function. Okay, so it's a theorem. If the approximate value function is linear, then value iteration with the distribution model loses nothing if you replace the distribution model with an expectation model. And here is the proof. First step is to replace the approximate value of the state you arrive in with its linear form, w times x of s prime. Oops. And then we pull this is really a linear form. Everything is multiplied times wt. We can pull the w transpose out and switch sides so it's no longer transposed. And this thing in brackets is then, look at it, it's the sum over possible next states, the feature vector for those next states. So that's the expected, damn it. That's the expected next feature vector. And so that's what an expectation model will give you the expected value of the next feature vector. And so this update is then the update with an expected thing, and it's equivalent. Okay. So I'm trying to propose the idea that the value function should be linear in the state features, and then we're golden with expectation models. So value functions being linear, you should be saying that looks like it's losing a lot of generality. But of course, it really doesn't, because we can always expand our state vector, our state representation, to do anything. I mean, just like if you have a complicated multi-layer neural network, still, if that's forming your value function, the value function is linear in the last layer. So it's linear in the representation that's been found in the last layer. So anyway, in the end, I don't think we lose anything by insisting that the value function be linear. It might even be advantageous. So to summarize this, I like to draw it in the shape. Some of you may recognize this diagram from the reinforcement learning textbook. There are 4 quadrants. They're each different kinds of planning. And they each can do full planning of anything you want. But I'm sort of suggesting that the little guy up in the upper right corner is the smallest form, and it's adequate, and we can just use it exclusively. Okay, so there's some thoughts on planning. Now let's go to subproblems. Subproblems in play. You might think about the whole landscape of reinforcement learning algorithms, and the simple, straightforward case, core reinforcement learning, we learn value functions and policies, and the next big step is to learn these larger things like state features and skills or options and models of the world. And the key all here is to formulate the subproblems. And what we see when animals and people play is things like this. We see this orangutan trying to do something as he swings. We see the orca playing with the bottle, very goal-directed. Cats are playing. Even lizards might play. And of course, young babies play. I really enjoy this little girl on the left who's just fascinated by the way her hands work. And in a few minutes she'll get a little bored with her hands. She'll start playing with her feet. But I think I'll just go ahead. And so we notice that there's a long history in AI of looking at subproblems that are separate from the main problem. Talk about curiosity and intrinsic motivation, really about this. And there's all kinds of issues. Let me just direct your attention to the things in red. And these are the key questions. Like, what should the subproblems be? And where do these subproblems come from? And how do the subproblems help the main problem? So very briefly, I don't want to dwell too long, but very briefly, there are 3 ways, and maybe the way that I'm going to focus on is that they enable planning to be better. Because we have a subproblem, we can form an option that achieves a subproblem, and then we can make a model, a dynamic model of what happens when I do that option, and then that is used for planning. So basically, subproblems let us as a structure for understanding the world and creating skills that achieve things, and then we can think about using those skills in various ways to achieve our goals. And this helps when states change their values. This is sort of true that if the states never change their values, then planning would be unnecessary. So remember, I keep talking about non-stationarity, like how it comes out of the large world and it's an inherent thing. And so let's get into non-stationarity. And I'd like to introduce a mechanism. This is the mechanism of permanent and transient memories when you're doing value function approximation. So these are my only equations, I think, in the talk. And you know the first equation. The first equation is just linear TD0. The weight vector is the new weight vector plus the step size times the TD error, like assuming the value function is linear, times the feature vector. Now, normally we would take the step size alpha small, and that these are what I'm calling the permanent weights. These are the ones that are going to gradually approach the best single approximation that averages over all states. And the idea of a transient memory is that we have a second weight vector, we're going to call it W tilde, and it's going to like fill in the bits that are missing in the permanent memory. So the only difference between the equations, well, here we have the permanent weights plus the transient weights. That's our new weight vector that's dotted with the state vector, okay? And these transient weights don't know anything about the other way around. These guys don't know anything about the transient weights, right? These guys are updated, there's no transient weights in sight. But the transient weights do know about the permanent weights, and they're kind of trying to fill in the parts that they're missing. So if the permanent weights are fine, they do the job, solve all the errors, then the corresponding transient weight will be 0. And if the world was totally stationary, then in the limit, the transient weights would be 0, all be 0. But because the world changes, and you might have a larger step size with the transient weights, they will converge to something, and they can greatly help. So, and I'm kind of running out of time, so I'm just going to do this very suggestively. If you try to assess this in Computer Go, and David Silver and Anna Koop did this some years ago, you find the various features, like shown here on the left, their value is different in different positions. And these two positions on the right are two positions in which the value of these two features are different. And so by using the transient memory, you can get these kind of positions correct, whereas if you just had the permanent memory, you wouldn't be able to. And so this is a head-to-head comparison on 5x5 Go of a player that uses just permanent weights and a player that uses both transient and permanent weights, and you get a clear winner for using transient weights. So it's good to think that values change, even if, as in Go, in some sense, if you could represent the value function exactly, it would not change at all. So, remember the 3 key questions about subproblems? What should the subproblems be? Well, let's start with actually the middle one. Where do the subproblems come from? So the idea is that the subproblems come from the state features. There's one subproblem for each feature, and so that subproblem will be trying to attain that feature while trying to get rewards in the normal way. And it will actually get a bonus when you arrive at that feature. So look at question number 1. What exactly should the subproblems be? Each subproblem should seek to maximize a single state feature and terminate at that time. And so we can just describe that formally in terms of a bonus for terminating where that feature is high, if that feature is a variable valued in terms of the transient weights. Okay, and then we can also see how these kind of subproblems and their solutions might help on the main problem, because we learn how to achieve various things that vary in value. So I'm all set. If they happen to be high, I know how to achieve them and I can plan to it. But if they're low, I don't have to. I can plan not to achieve them. Okay, good. So the summary of this approach, based on subproblems and features, the summary of the approach is that to be a capable agent, you have to learn larger things. You have to learn state features. State features have to become more and more abstract. You need to have options to achieve important things in the world described by those possibly abstract features, and then you have to learn models of those ways of behaving. So state feature attainment, while respecting the rewards, I'm not changing the rewards, it's a distinctive kind of subproblem, and I'm arguing today that it fits well into planning and representation learning. Because the world is big, we have to approximate it. That means it appears to change, we have to track it. That's why planning and generalization makes sense. And the changes in the approximate value function tells us which features should be the focus. Okay, so we're really coming down to the end. I can't really tell you, okay, I'm going to show you Super Dyna. Super Dyna ambition, the idea is to put everything together in one single page pseudocode. So here it is. So this is the ambition. I can't quite have it fully explained. Actually, I had to put a little bit on the next page. But just a little bit. And then there are a couple pieces that are like templates. The 4 basic steps: you interact with the world, and then when you're done interacting. So this loop here is the inner loop of the agent. Like, these are things that are done every instant. Every, say, 10th of a second or 100th of a second, you do these things. And then you're like an engine. You can blum, 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 keep doing this thing. And that's all there is to it. And those things you do, you sense, you do state update, you take an action, and then you learn from what just happened. You see what happens, and you learn from it. Those are the things in red. And then with the leftover time in that time step, you do planning. You imagine hypothetical states and actions you might take in them. The 4th step is discover, is where you curate the options and the features. We curate the features, you add features, remove features, generate new features, and you just measure how well they're doing. Because every once in a while you take a feature that you've had for a long time, you throw it out. And every time you take a feature that you've had for a while that has proved useful, and then you make a new subproblem for it. You can also evaluate the options by how useful they are in planning, and then remove things or add things to the set of options. Okay, I'm done. So these are all steps towards the first complete AI agent architecture that has all the most important capabilities and desiderata. So this is my list. Obviously, like in 1990s Dyna, we need to act and learn and plan and model learn all at the same time. We also need to have subproblems and options. We also have to have function approximation, partial observability, non-stationary, and stochasticity. And the most special thing here is that we can discover all these elements. We can discover the state features, and from that discovery of the state features, we automatically get subproblems, options, and models. As we work on each one of these parts, we're making more and more prediction problems. We're having to solve or learn more and more general value functions, and those all evaluate our choice of features. So really all these subsequent steps evaluate the choice of features and direct you to consider more and more abstract features so that we get a real cycle of discovery. Okay, so this thing we're reaching towards is Super Dyna. Would be the first complete AI agent architecture that has all the most important capabilities and is completely general. There's nothing domain specific. There's nothing domain specific anywhere in the whole thing, and thus is potentially scalable and of lasting import. Thank you very much. Now, I think we're going to have a panel.
Thank you, sir. Here, let me get